Hello again, welcome to Basics of Noise and its Measurement. We have been discussing, starting last class, this concept of Fourier transform, and we have not yet completed that treatment. So what we will do in this class is complete the discussion on Fourier transform, develop some explicit relations for Fourier transform, and then see what they mean from a physical standpoint. What is the physical interpretation of these transforms? So that's what we plan to do in this particular lecture, and let's see how it goes. So in the last class we had developed this relation that f of t. So f of t is a time series function, which this particular function does not have to have a finite time period, and that can be expressed in this somewhat longish format, and where it is equal to 2 over pi integral 0 to infinity integral of fv cosine omega t minus omega v dv times dw, and this entire thing I am calling it as the integrant. This whole thing I am calling it as f of omega d omega. Okay. So let's call this equation A. So I will write the expression and then I will define GW. So this expression is 1 over 2 over pi 0 to infinity 0 to infinity, and here I am having f of v, and instead of cosine I am having a sine term omega t minus omega v dv d omega. Okay, and what I am going to define is that this entire thing this is GW. So GW's definition, and of course it has to, so GW's definition is pretty much same as that of FW, but instead of cosine function I have a sine function. And here I am going to straight away say that this is equal to 0, because this sine is an odd function, and if you go to our earlier discussion, you will find that if you do the requisite math, you will find that this thing is 0. So if this entire thing is 0, then if I add this to f of t, I still get f of t. So my expression for f of t equals 2 over pi 0 to infinity f of w plus I will write g of w, and I am going to integrate it with respect to, so actually not w, I will call it omega, because a lot of times we use this for angular frequency. So this expression is valid, and now what I will do is if I multiply it by some constant where I equals the square root of minus 1, then still this expression is valid. Okay, so this is equal to 2 over pi 0 to infinity f of v cosine omega t minus omega v plus I sine omega t minus omega v. This entire thing has to be multiplied by dv, and it has to be integrated, and if you go back, so this has to be integrated with respect to dv, and then there is d omega. Okay, this expression I can write it as e to the power of I omega t minus omega v. So what I get is 2 over pi 0 to infinity f of v e to the power of I omega t minus omega v dv d omega, and this is also being integrated. What I can do is I can change these limits, so I can make this 1, and here I have minus infinity, and I still get the same thing. So now we are pretty close to the Fourier transform, and I can change the limit again. So these limits were 0 to infinity, and if I make this minus infinity to infinity, then I have to make it 1 over 2 pi. Okay. So now what I do is I again further transform this relation, and I make this 1 over square root of 2 pi integral minus infinity to infinity, and then I again inside the integral I multiply it by square root of 2 pi minus infinity to infinity f of v e I omega t minus omega v d omega. And what I do is I further modify it minus infinity to infinity 1 over square root of 2 pi minus infinity to infinity f of v, and what I do at this stage is that here I separate omega t and omega v. So this is I omega, so I had missed here, this was dv and d omega. So e omega t and e omega v. So if so e omega v dv, and then e omega t dt, d omega. So this is the Fourier transform. And we will actually explain what all this is about. So this is the Fourier transform relation, and I can call this entire expression, which is in parenthesis, as f hat of omega. So f hat is a different function than f. So I can express ft as 1 over square root of 2 pi integral minus infinity to infinity f of omega d omega hat, right, where yes, e raised to the power of I omega t d omega, where f hat is 1 over square root of 2 pi minus infinity to infinity dv. So what does this first relation tell us? Actually, we'll first look at the second relation, that if I have a function of time Okay, V could be time. If I have a function of time, I can convert it into the frequency domain using this relation for f hat. So this helps us convert time domain signal into frequency domain signal. And the first relation, if I have a frequency domain signal, then I can back convert it into the time domain signal. So that's why it's known as inverse transform. So this helps us transform frequency domain signal to time domain. So this one is also known as inverse transform right. Second one, that's known as inverse Fourier transform. The first, and this guy is actually your Fourier transform or direct Fourier transform. So if you have a time series signal, and again this is not a digital signal, so we are not having discrete points. If I have a continuous function, of time, and that function is not periodic, and I still want to figure out what are its frequency components, then I use this second formula, and using this I can calculate its frequency components. And suppose I have frequency components and I want to make a time signal out of it, then I use this first formula, which is the inverse transform, and using that I can calculate or generate a time signal out of it. So from time I can go to frequency, from frequency I can go to time, and I can do this back and forth. So this is what this Fourier transform helps us do. The second thing I wanted to explain you is that there is this exponent to the e to the power of I omega v and e to the power of I omega t. These are here. What that tells us is that when you do this calculation, you will have a complex part, an imaginary part, and a real part. And that information will help you compute something more than just these numbers. For instance, when you are in the frequency domain, and if you have a complex part and an imaginary part, a real part and an imaginary part, you should be able to, using that information, able to compute the phase information about a frequency component. So suppose there is a frequency component and you have an imaginary component, imaginary fraction of it and real fraction of it. Take the ratio of those two, and that will give you the phase information. And you take squares and add them up, that will give you the magnitude. So you are able to calculate phase information also using this approach. So this is the overview of Fourier transform, and what we will do in the next week is that we will actually do some examples, but not in context of some analog signals. So all this information is valid only if signals are continuous, or at least discrete, piecewise continuous. But when we take data from actual instruments, we don't get continuous data, we get data at different points, discrete points. So how do you convert that discrete data, which is a function of time, into frequency domain, is something we will discuss, and actually we will do some examples in the next class and learn that. So with that, I want to close my lecture for today and also this week's lectures, and I look forward to seeing you tomorrow. Thank you very much. Bye.